So in the previous video, we studied about the perpendicular axis theorem, which is a theorem which is valid only for laminar bodies or 2D structures. But what if we are given with a 3D structure like this? What if we are given with a 3D body? Is there any axis theorem for that too? Yes, indeed there is. We have a theorem known as the parallel axis theorem. And the good news about the parallel axis theorem is that it is applicable for all kinds of rigid bodies. Whether it is 2D or 3D, it is applicable for all of them. So let us start understanding this particular theorem. Consider this particular rigid body. Assume that this particular point is nothing but the center of mass of this rigid body. And this axis is an axis which is passing through the center of mass of this rigid body. Now, let us assume that the moment of inertia of this rigid body with respect to this particular axis, which is passing through the center of mass, as IC. Now, we consider another axis of rotation which is parallel to this particular axis which is passing through the center of mass, and we assume that the distance between these two axes, this axis and this axis, is d. So, according to parallel axis theorem, if the moment of inertia of this rigid body with respect to the axis passing through the center of mass is IC, and if the moment of inertia of this rigid body with respect to this axis is I and IC can be related by this relation. So how do we obtain I from IC? So if we know the moment of inertia of this rigid body with respect to this particular axis, that is IC, and if we simply add a term of md squared, where m is nothing but the mass of the rigid body, we can obtain the moment of inertia of this rigid body with respect to this particular axis, and it is given as I. So what is parallel axis theorem? I write again. I and IC are related as I equal to IC plus md square, where m is the mass of the rigid body. Now let us try to look how this particular theorem is proven. Let us consider this particular figure. We have the center of mass here. This is an axis which is passing through the center of mass. So the moment of inertia of this rigid body with respect to this particular axis is IC. And we are assuming that the moment of inertia of this rigid body with respect to this axis as I. Now we are considering an elemental mass here. Let us call this small elemental mass as dm. Let us call this particular distance as r. And let us call this particular length, that is the distance from the center of mass to the elemental point mass, we are assuming as rc. Now let us consider the plane that is formed by these two particular vectors r and rc. We are considering this particular plane. In this particular plane, we try to take the components of rc along this particular direction and this particular direction. So one direction, that is this direction, is along the line joining these two particular axes, and this particular direction is perpendicular to it. So this length is rc sine theta, and this particular length is rc cosine theta, where this particular angle is theta. Now the distance between these two parallel axes is d. So we can clearly write r square is nothing but rc sine theta whole square plus d plus rc cos theta whole square. This is simple Pythagoras theorem. That is, the square of this particular length is nothing but the sum of square of this particular length and this particular length, because this is a right angle triangle. So what do we get? We get r square as rc square plus d square plus 2rcd cosine theta. So what is I? I is the moment of inertia of this rigid body with respect to this particular axis. So I would be simply integral of dm times r square, as the distance of the elemental mass from this particular axis is r. Similarly, what would be IC? IC would be simply integral of dm rc square, as the distance of this elemental mass from this particular axis is given as rc. So let us use these two equations. So I is integral of dm r square. Now let us use this particular equation in this equation. So this reduces as integral of dm times rc square plus d square plus 2d rc cosine theta. So what do we get? We get integral of dm rc square plus integral of dm d square plus 2d times integral of dm rc cosine theta, as d, that is the distance between these two particular axes, is a constant. So what is this particular term, that is integral of dm rc square? This is nothing but IC. Integral of dm rc square is nothing but IC. So this term is IC. How do we simplify this particular term? Integral of dm d square. As d square is a constant, we can write it as d square times integral of dm. What is integral of dm? Integral of dm is nothing but the total mass of this rigid body. Let us assume that the total mass of this rigid body is m. So integral of dm d square would be nothing but md square. Now let us try to simplify this particular term. Understanding this is very important. Now what is this particular term? If you recall from the previous chapter of center of mass, if this point is considered as the center of mass of this rigid body, then with respect to this particular point, integral of rc vector dm would be 0. That is, if we consider lots of elemental masses which are located at radial distances rc, then the integral, that is this particular equation, generated by considering all the elemental masses in this rigid body located at various radial distances, would lead to 0. That is, if we split the radial distances in two mutually perpendicular directions, let's say this direction and let's call this direction as x, and if we consider y-axis which is parallel to this particular direction, let's say this as y, then the component of this particular radial distance vector along the x-axis and y-axis would be simply rc cos theta and rc sin theta. So we can write from this particular expression as integral of dm rc cos theta equal to 0, or integral of dm rc sin theta equal to 0. If this portion is not clear, you can write to me, you can contact me. My contact is given in the description. Anyways, when I will upload the videos on the topic of center of mass, which I will do very soon, all these things would be explained in detail. Till that time, feel free to write to me. So, integral of dm rc cos theta is equal to 0. So, this term is equal to 0. So, this particular expression would be nothing but 0, as this particular term is 0. So, what do we get? We get I, which is nothing but dm r square, as it reduces to IC plus md square. So, that is how we prove the parallel axis theorem. So, let me write this theorem once more. That is, I is equal to IC plus md square. So, if we are given with a rigid body, and if this is the center of mass, and if with respect to this particular axis which is passing through the center of mass, the moment of inertia is IC, and if the moment of inertia of this rigid body with respect to this axis is I, and the mass of this rigid body is m, and the distance between these two axes is d, then I would be given as IC plus md square. How do we define the distance between two axes, this and this? We define the distance between these two axes as this line joining these two axes, which is perpendicular to both of these axes. That is, this is perpendicular to this particular axis, and this is also perpendicular to this particular axis. Similarly, if we have the axis tilted like this, and if the moment of inertia of this rigid body with respect to this axis passing through the center of mass is IC, and with respect to this axis which is parallel to this particular axis is I, again I would be equal to IC plus md square. Similarly, if the axis is oriented in a different manner, and if the moment of inertia of this rigid body with respect to this axis is IC, which is passing through the center of mass, and with respect to this axis which is again parallel to this particular axis is I would be simply equal to IC plus md square. So, for applying this particular theorem, which is the parallel axis theorem, we need an axis which is passing through center of mass of the rigid body, and another axis, that is this axis, should be parallel to the axis passing through center of mass. So this is clear, this is simple and easy. Now let us try to look into few applications of the parallel axis theorem. So here we are given with a ring of mass m and radius r. So the center of mass of a ring is located at its center. So this is the center of mass. And in the previous videos, we already calculated the moment of inertia with respect to this particular axis. So we already know IC. So IC is simply mr square. Now we wish to calculate the moment of inertia of this ring with respect to this particular axis, which is parallel to this axis. Let us assume that the moment of inertia with respect to this axis is I. So I would be IC plus md square. Now what is the distance between these two particular axes? It is simply r. So let us substitute the values. IC is mr square. What is d? D is nothing but r, that is the distance between these two axes. So mr square plus mr square. So what do we get? I is nothing but 2mr square. Simple and easy. Now let us say we place the ring horizontally. So this is the center of mass of the ring. Now the moment of inertia of this particular ring with respect to this particular axis, let's call this as IC. So what is the value of IC? We calculated this already just in the previous video. IC is nothing but mr square by 2. So what is the moment of inertia of this ring with respect to this particular axis? Let's call this as I. This axis is parallel to this axis. So I would be nothing but IC plus md square. What is IC? IC is mr square by 2. What is d? D is nothing but r. So mr square by 2 plus mr square. So I is nothing but 3 by 2 mr square. Simple, easy again. So now let us try to calculate the moment of inertia of a disk with respect to some axis using the parallel axis theorem. So we are given with a disk of mass m and radius r. So this is the center of mass of this disk. This is the center of mass of this disk. This is the center of mass. So the moment of inertia of this disk with respect to this particular axis, which is perpendicular to the plane of the disk, is IC, because this is an axis which is passing through the center of mass of the disk. Now we are considering an axis which is parallel to this axis, and we are calling the moment of inertia of this disk with respect to this particular axis as I. So what is I? I would be simply IC plus md square. What is the distance between these two particular axes? It is simply r. So what is IC? We calculated the moment of inertia of a disk with respect to this particular axis as mr square by 2 plus mr square. So what do we get? We get the result as 3 by 2 mr square. Similarly, if we try to calculate the moment of inertia of this disk with respect to the axes which are lying in the plane of this disk, so we are given with a disk of mass m and radius r. This is the center of mass of this disk, and as this axis is passing through the center of mass, this is going to be IC. And let us assume that the moment of inertia with respect to this axis as I. So these two axes, this axis and this axis, are parallel, and one of the axes is passing through the center of mass, so we can apply the parallel axis theorem. So I would be nothing but IC plus md square. So what is IC? We already calculated IC in the previous video. It is nothing but mr square by 4 plus, what is d? D is nothing but r, that is the radius of the disk. So mr square by 4 plus mr square. So what do we get? 5 by 4 mr square. Simple, easy, straightforward. Similarly, if we are given with a hollow sphere, where is the center of mass of a hollow sphere? It is nothing but the center of this hollow sphere. Clearly, the moment of inertia of this hollow sphere with respect to this axis is IC. Now, what if we wish to calculate the moment of inertia of this hollow sphere with respect to this particular axis, which is nothing but a tangential axis of rotation? So this axis and this axis are parallel to each other, and this particular axis is passing through the center of mass. So I would be simply IC plus md square. Let us say that the mass of this sphere is m. So what is the distance between these two particular axes? It is nothing but r. So what is IC? IC is nothing but 2 by 3 mr square. We have already calculated it long back, plus mr square. So what do we get? We get it as 5 by 3 mr square. Similarly, if we are given with a solid sphere of mass m and radius r, and we wish to calculate the moment of inertia of the solid sphere with respect to this particular axis, which is nothing but a tangential axis. Clearly, again, the center of mass of the solid sphere is nothing but its center, and this is nothing but IC. So I would be simply IC plus md square. What is d? What is the distance between these two particular axes? It is nothing but r. So what is IC? We have already calculated it. It is nothing but 2 by 5 mr square plus mr square. So what do we get? We obtain the moment of inertia of a solid sphere with respect to a tangential axis as 7 by 5 mr square. So we can see that applying this particular theorem, which is the parallel axis theorem, is very simple. It's very easy. It's lightning fast, and it's simply straightforward.